All right, let's talk about I and what it tends to do to complex numbers. So what I'm going to do is I'm going to draw a coordinate plane that's going to represent the complex plane. So we're going to have the imaginary axis and the real axis. And let's make some number, a plus bi, and let's draw it on the complex plane. All right. And what I'm trying to show for you guys here is that when you take this number, a plus bi, and you multiply it by I, that is, you take any complex number with a, which are real numbers and their coefficients, and you multiply it by I, you will get a new complex number. Let's label it c plus di. That is a 90 degree, that is simply a 90-degree rotation counterclockwise around the origin of the original complex number. So if you ever dealt with complex numbers, or if you've worked with them in high school, sometimes you'll hear that I has a tendency to rotate things about the complex plane. And if you ever wondered what that meant, this is what it means. If you take a number in the complex plane and you multiply it by I, what you end up getting is a new complex number. There's a 90-degree rotation of the original one. And I'm going to prove that for you really quickly. So if we expand a plus bi times I, right? So if we want to rewrite c plus di in new terms, because we know that we're just taking our original complex number and multiplying it by I, what we're going to get is, if you expand it, you're going to get ai minus b, because the I here is going to go in and multiply with the bi to get bi squared, and I squared by definition is -1. So you get minus b as the real part, and the I goes into the a, and you get ai. So we have a new complex number that is ai plus b, which in our example above is equal to c plus di, or in other words, is our new complex number that's been multiplied by I, and we're trying to show that that's a 90-degree rotation of the original number. So what I'm going to do is I'm going to first draw a few things to label the first complex number. This is A, and this is B. All right, so if our new number is ai minus b, right, it's A in the imaginary axis and negative b, so it goes back, b in the real axis. All right, so what that means is we'll point here where this is A and this is B. All right, and this is very, very poorly drawn. All right, so don't worry about how poorly drawn it is. We're just going to prove it mathematically. All right, so our first step, if things are going to be a rotation of another point about the origin, the points have to be the same distance from the origin by definition. So our first step is to show that distances are the same. All right, and we can find the distances between the origin and the points using the Pythagorean theorem. So for this point right here, the distance is going to be the square root, and we're not going to say plus or minus because distances can only be positive, so it's just plus. So it's going to be the square root of b squared plus a squared. And although a squared looks like it's representing the hypotenuse here, it's actually representing the vertical distance. So I should probably draw that a little better. This is what a represents. So the hypotenuse is a squared plus b squared, and the square root of that. All right. And the other one is a squared plus b squared as well. Or the square root of that. I apologize. All right. And these are the same. So we just proved that these 2 points are the same distance from the origin. So that's step 1 complete. Now what we want to do is we want to prove that this is congruent. And you can do that in 2 ways. Perhaps the easiest way is, I'll just tell you the quick way. I'm going to do it a different way. But the quick way is to notice that the slope of this line, right, rise over run, is A over negative B, or negative B over A. All right, because the B extends in the negative direction. All right, and the slope here is B over A. And these 2 slopes are opposite reciprocals of each other, so they're going to be perpendicular. These 2 lines are perpendicular, and we know they both intersect at the origin, so this angle is 90 degrees. That's the easy way. Another cool way you can do it is, I'm going to go to another tab here. You can do this. I'm going to draw out I'm going to draw our original triangle. Sorry, my dog is going crazy. All right. So we said that this length, right, is the square root of a squared plus b squared. And this is our point. This is the origin. This is our unrotated point. All right. And we said that this length is also a squared plus b squared. And I'm going to draw our coordinate system out again, where this is real and this is imaginary. All right. So we can find this length using the distance formula, which is that the length of this segment is going to be equal to the square root of this y coordinate, so y2 minus y1 squared, plus x2 minus x1 squared. That's the distance formula, and it just derives from the Pythagorean theorem. So when we do that, I'm going to draw our lengths once again. So this is b, this is a, this is b, and this is a. All right, we're going to get the square root of a minus b squared, all right, plus the square root of, in the x direction, the x change here is a plus b. So we get a plus b, or sorry, not the square root of that. What am I doing? I meant to say plus a plus b, that distance, squared. All right, and what you can do here is you can actually simplify things a little bit by expanding the two terms. What you'll end up getting is if you expand this term and this term, you'll get 2a squared plus 2b squared. And that's because, remember, when you expand a minus b squared, you end up getting that negative 2ab term. And when you expand a plus b squared, you end up getting that plus 2ab term. So these terms cancel. And what you're left is simply the a squared plus b squared in here and the a squared plus b squared in here. So there's 2 of each. So you get 2a squared plus 2b squared. And we're going to do things, we're going to take things a little further, and we're going to say this is equal to, so remember, this is all under square root. So it's going to be square root of 2 times a squared plus, I think that's a plus. Yes, it's plus b squared. All right. So I'm going to do another step. And I'm going to go to the next slide here and say that this is equal to, just from the rule that the square root of a times b equals the square root of a times the square root of b. This is equal to root 2 times the square root of a squared plus b squared. And now, just for convenience sake, because this is a lot to write, I'm going to say, let's say this equals gamma. All right, which is just a fancy Greek letter. All right, so our new triangle then has side lengths of gamma, and root 2 gamma. All right, and if you know anything about 45, 45, 90 triangles, this is actually a 45, 45, 90 triangle, where these two sides are equal and the other side is equal to root 2 times one of those sides. So deduce from that, we can conclude that this is a 45, 45, 90 degree triangle. And this angle right here has to be 90 degrees. So that's another way that you can prove that that angle is 90 degrees. The angle bound by rotation is 90 degrees. So what we ended up proving is that if you take, this is the kind of takeaway here, is if you take any complex number, a plus bi, and you multiply it by I, you generate a new complex number, c plus di, which really equals ai minus b, if you expand this. That is just a 90-degree rotation counterclockwise of the original complex number. And the cool thing is, this also works for any pure imaginary number in the form of bi and any pure real number that's written as a, because this generalizes that case too, because in this case, it's just this. I'm going to do this. In this case, it's just this, where a is equal to 0. In this case is also this case, b is equal to 0. So this case actually generalizes complex numbers, pure imaginary numbers, and pure real numbers. So any number multiplied by I rotates it 90 degrees. And the reason this is important is because you can actually show, or sorry, I'm going to actually show that e to the I pi plus 1 equals 0, using this idea that I tends to rotate things 90 degrees counterclockwise. And there's a cool example where if you have a position vector that's e to the x, or e to the ix, then your velocity vector is going to be I times e to the ix by the chain rule, which is your original vector multiplied by I. And we said I has the tendency to rotate things 90 degrees. So your velocity vector is going to be equal in magnitude to your position vector, but just rotated 90 degrees. And that's why e to the ix tends to trace the unit circle, the complex unit circle. And that's why when you go pi around, you get -1 and then +1 is equal to 0. So the reason this is important is because it provides a lot of insight into other rules regarding complex numbers, and this is perhaps the most elegant equation in all of math. And you can use it or prove it using the idea that I rotates things 90 degrees. So that is it for today. I hope you enjoyed, and I'll see you guys in another time.